Okay, so my name is Sam. I'm the team captain of Strathloop. I have been since the start of 2020. I'm now in my master's year of mechanical engineering at the University of Strathclyde in Glasgow, the UK. And last year, as part of my undergraduate thesis, I designed a Hyperloop Airlock system, did some work in the world of vacuum systems design, which I found really interesting. I continued some of that work on through the summer, and I'm very thankful to be able to share some of my findings today, share the design and some of the methodologies that I used in creating it. If there's any questions about the presentation that you think of after, I've just left my email there as well. So fundamentally, the sensible place to start is what actually is a Hyperloop airlock system and what does it need to do. The airlock is essentially the device that's used to take the pressurized cabin of the pod filled with passengers or cargo and to move that in an effective manner to the station environment, of course, without any of that passengers or cargo being exposed to the low pressure tube environment for fairly obvious health and safety reasons. There's some key performance variables that I identified at the start of the process that characterize a good airlock design. Of course, as with anything in engineering, costs, money makes the world go round, and it being a fairly cheap system to implement was a fairly major factor. The throughput, this is in effect how many passengers or how many kilos of cargo can the airlock actually service for a given time frame. This is actually a really important factor because more often than not, the airlock is a sort of pinch point within the flow of passengers or cargo in and out of the station. The energy consumption as well is another major factor, especially for certain types of designs. This is dominated by the energy requirements of vacuum pumping. If you're cycling volumes of air between the atmospherically pressured station environment and the low pressure tube environment. And when I say low pressure, I was working with a tube pressure of around 100 pascals, which is the norm among most of the published pressures that current Hyperloop companies are working around. And of course, whenever you're working with any system with a lot of human interaction, and especially with the interface with the vacuum system, safety was of utmost importance. So from there, I wanted to have a look at some of the existing designs, and I'll go over some of these in the next 2 or 3 slides. They fall into 2 main categories, the first of which is airlock chambers. This is probably the simplest form of airlock system. What you can see on the 3 diagrams here is the sort of 3 main phases. So you have the pod, which will approach through an open gate valve and come into this chamber section where both gate valves will be closed and the air inside this chamber here, if you can see my mouse, will be cycled between the low pressure tube environment, will be repressurized to the station environment, and from there that second gate valve will open. Because it's got 2 fairly simple gate valve sort of tube sectioning devices, the redundancy of the system is quite simplistic. It makes it quite a safe system. However, because you're having to evacuate such a large portion of air, the pump down times and the energy requirements of that pump down does take quite a long time. So the other main form of airlock systems at the moment is docking methods. So in this form of airlock design, the pod approaches a series of docking ports, and these interface directly and create a pressure seal directly between the pod body and some external face of the tube. This creates a door cavity which can be pressurized, and these cavities are far smaller, as you can imagine, than the full airlock chamber. And then once that pressure is equalized, the doors can open and the passengers can enter or exit as safely as possible. The as you can see, there's a lot less volume of air that requires vacuum pumping, so the energy requirements and the pump down requirements are far better. There is a concern of safety with these methods, the fact that the low pressure environment is very close to passengers for quite a large proportion of the airlock cycle. And they are potentially quite expensive because if you think about it, the pod as it comes in has to remain interfaced with the airlock at all times, where with the airlock chambers, it could come in, be sent fully into the station environment, and then that same airlock could process another pod while the first pod is still going around the sort of station process. So potentially very expensive because you'd have to have lots of these systems to get the throughput that you would want. So I did a little bit of systems analysis on some of the existing systems, and the airlock chambers, as I said, are relatively poor in their energy consumption and their throughput, but they do have very good cost and safety, whereas the docking systems offer, in effect, the complete reverse of that. So it leaves us with this dilemma. How do you, or getting an airlock method which minimizes the pump down times without requiring that one-to-one airlock pod ratio. So that really was the silver bullet solution that I was aiming to produce with the design of my airlock system. And this is how we arrive at the push-through airlock. Now this is inspired quite heavily by medical catheters. A medical catheter is a device which holds a permanent seal between normally an environment that contains your bloodstream and then the atmospheric air, but it can allow an object to be pushed through that seal. So it uses a combination of a permanent seal or a solid seal and these rubberized temporary seals. And on the push-through airlock acts very similarly with the Hyperloop pod approaching it. So it has this central gate valve which will open when the pod is approaching and has already engaged with these sealing vanes, which are the rubberized sealing vanes. Once they've been engaged, the pod will continue moving through, the gate valve opens, and these sealing vanes maintain the pressure difference between the station environment and the tube environment, and then as soon as the pod is through, the gate valve can close again. So this allows the pod to move through into the station environment without any lengthy pump down times, and because it's moving fully out with the airlock system after, we can have multiple pods serviced in parallel by a single airlock system. So I moved on to the detailed design of this, and I designed the main pressure vessel of the airlock section. I followed the British standard PD 5500, which is the pressure vessels design code for the UK. There are similar American codes within ASME. And the primary method of failure that I identified was elastic buckling. This was due to the fact that the pressure inside the vessel was less than the atmosphere outside, so it was almost like being crushed, if you imagine like a can being crushed and buckling in. So the analysis you can see in the top left-hand side here is the minimum safety factor on the y-axis and the thickness of the tube wall of the pressure vessel. And each of these lines corresponds to a different unsupported length. Now what that means is that periodically along the tube there will be interstiffeners to protect against this buckling phenomena. And what I managed to do was to optimize the design of the vessel such that the thickness and the interstiffeners gave us a suitable factor of safety. You can see here, as per the design code, I used 1.5 on the yield strength of the material. I also included this taper section going down from the main tube, which has to be quite large in relation to the pod because of the high speeds that you're traveling at, to overcome or to increase the velocity of the Kranovitz limit. Of course, in the airlock section, that's not important because we're not going to be moving at those high speeds as we come into the station. So I tapered it down, and that reduced the volume of any leak there and made interfacing with the pod for the sealing vanes far simpler. From there, I focused quite a substantial amount of effort on the temporary sealing vanes. This is by far the most complex component within the airlock system, and it really is the unique part of this airlock design. So I performed 2D axisymmetric, transient, implicit, finite element modeling for the sealing vane interaction with the pod. So what you can see here is my sealing vane, which is a sort of big block at the top. And then this thin shell down here, that is the outer surface of the pod. And I had the pod coming in at 5 meters per second. And I didn't employ any multiphysics at this stage. I purely looked at the contact pressure as a means of success criteria for the seal of the pod. I used the safety factor of 2 on the vacuum pressure between atmospheric pressure, and that gives 200 kilopascals, and I used a coefficient of friction of 0.2 between the polished pod surface and the rubber sealing vane. So if I play this video here, you'll see a sample simulation of the sealing vane moving along the pod surface as it moves through. And I then looked to optimize the design of this sealing vane. So I identified 4 main parameters of the sealing vane design, which itself was based on hydraulic rod seals and scraper seals. So the stiffness of the rubber, of course, being a key factor. The compression, so that is the difference, the distance between the bottom of the sealing vane and the top surface of the pod. Here, the vane compression parameter. The sweep angle, that is the angle between the vertical plane and the angle of the actual contact vane, and then the vane thickness, of course, the thickness of that vane itself. I found that increasing the logical conclusions of increasing the compression distance, the vane thickness, and the shear modulus increased my the contact pressure quite substantially. What I was not necessarily expecting through the optimization was how sensitive it would be to sweep angle. Increasing the sweep angle massively increased the contact pressure, but it also massively increased the stress and the strain on the component. So I ended up with a fairly shallow sweep angle of only 120 degrees for my optimized design. I used ANSYS Design Explorer with a MOGA algorithm setting to achieve this, and my final vane design, I got above the contact pressure requirement that I'd set with a very small amount of von Mises equivalent strain. But looking at the final airlock parameters, the velocity of the pod was 5 meters per second, as discussed already. Now, given that the airlock chamber has this airlock that needs to go up and down and reset, the maximum departure rate that the airlock system is able to cope with is 65 pods per hour, which is very competitive next to a lot of the other. I know that Delft did a design a few years ago that got 60. And the energy consumption was only 4.669 kilowatt hours per pod departure, and you can see here in the orange the results of the two systems in relation to some of the existing systems that I discussed earlier. So it performs incredibly well in the throughput side of things, and also incredibly well on the energy consumption. In terms of cost, because you'd only need one system as well, it's incredibly beneficial from a cost standpoint compared to some of the docking systems. The one key thing at the moment is, of course, the safety of the system. This temporary vane is quite an untested thing at the scale that we're talking. Most reciprocating seals tend to be used in like hydraulic actuators, and they're fairly small, and they're used to maintain seals between fluids that are far more viscous than air. So from there, that is effectively the final design of the airlock system that I created. Of course, there's still lots of steps that myself and others within Strathloop are looking at to make this better. So we would like to perform some testing on this temporary sealing vane in a physical setting. It's something in the next couple of years we'll be looking to build a small-scale prototype of the design. One of my colleagues, Matthew McDowell, is currently designing a tube section device akin to the gate valve that I discussed earlier. And we want to look at some more life cycle testing of that sealing vane because it will have quite an important role in the feasibility of the airlock design moving forward. And the main ones that I identified there was abrasion, and then after that, the fatigue of the rubber. So that's my airlock design. It's been a pleasure to present to you all today. If anyone has any questions, I would be very happy to take them.
Yeah, thank you for your presentation. If we have any questions, feel free to type in the chat or unmute yourself. We don't have any more questions. I think we'll wrap it up here. Thank you so much for the presentation. That was great.
It's all right. Thank you very much again for having me. It's a pleasure.
Thank you.